Hello and welcome to the sixth tutorial in this series on calculus at the higher level. And in this tutorial, which is really optional, I would say, I'm going to give a derivation of the result that we looked at in the previous tutorial, namely that the derivative of sine x is cosine of x, and the derivative of cosine of x is minus sine x. I stated that result in the previous tutorial, but we had motivated it quite carefully using a graphical analysis. Here I want to prove it because actually we have the tools to hand to prove this result, and because we have those tools to hand, I think we actually are honor bound to prove it. It would seem really odd for us not to do that, given that this is mathematics and not, origami. We are going to be very logical and systematic, so that every step we take, we're very certain of the steps that we've taken before, and that is the subject of mathematics. It's going to be, I think, a slightly tricky tutorial because the proof is not entirely straightforward. If we knew a little bit more mathematics, we could make simpler proofs, but I'm trying to use the tools that we have to hand, so it's going to be slightly indirect, but I think it will be fairly rigorous. It's going to bring together some of the early discussions on calculus we had, where we talked about the definition of the derivative. It's going to bring in the concept of radians, and it's also going to bring in use of the addition formulae from trigonometry that we talked about recently as well. So in a way, possibly satisfying that we're bringing together certain things. So let's start with the more formal definition of the derivative that we have already seen a couple of times in earlier calculus tutorials. So the derivative of a function f of x can be understood as the difference in the output of the function between 2 points which differ by just a small difference in x, which we call delta x. So this is really saying that the derivative is the ratio of the output of the function at 2 points which are closely separated by a value delta x. It goes all the way back to that original idea of the derivative connecting a change in input to a change in output. And formally speaking, we want to take this change in input, this delta x, to 0. All right. So all of the action is in this term here. That's what we have to focus on, and in previous tutorials when we looked at x to a positive integer power, we found nice ways to study this and pull out the leading term in delta x. That's what we want, because all the higher terms in delta x squared and delta x cubed and so on are irrelevant for this derivative, because once we divide by delta x and take delta x to 0, all those higher order terms will vanish. So let's start then with defining our function. F of x is the sine of x, and we're implicitly now thinking of x as an angle measured in radians. So in other words, if x has the value 0, sine of x is 0. If x has the value pi, sine of x is 0. If x has the value pi over 2, sine of x is 1, and so on and so forth. And okay, let's just plug that into our formula here for the derivative. Well, remember the f of apple discussion going all the way back to those functions videos. We have f of the argument x plus delta x. So for this particular function, that's sine of the argument x plus delta x. And then take away f of x, which for us is just sine x. And then all divided by delta x. And I'm not going to keep writing this bar delta x going to 0, but we'll just implicitly understand that we're interested in arbitrarily small delta x, and eventually we want to take delta x strictly to 0 and see what's remaining, and what's remaining will be our derivative. Now you can see already probably that to make any progress we have to do something with this term, and you can see that's the addition formula coming right in at the beginning here. This is like sine of a plus b. Our angle A, as it were, is x, and our angle B, as it were, is delta x. So using the addition formula, we have this as sine of x times the cosine of the second angle, delta x, plus cosine of the first angle, x, sine of the second angle, delta x, and then take away sine x at the end, all over delta x. That's fine. Now here comes the question, what do we do now? Because actually, having used the addition formula, which has helped a bit, but it's not entirely obvious what we're going to do with the sine delta x and cosine delta x. And this is where we have to be quite clever. There's a way to make progress very formally, just using our knowledge of the kind of the graphs of sine x and cosine of x. But I thought about using that, and it's a little bit stiff and formal, and I'm going to prefer to use a geometric proof from here on, actually, which I think you'll enjoy more, and it's more intuitive. I think you'll see how radians comes in more explicitly. So in that, to proceed then, I need to draw a picture. And I'm going to draw this quite carefully. I want to essentially draw a sort of a magnified picture of a very skinny angle, big enough that we can see what's going on, but with an angle small enough that we get an intuitive sense of what it means to have a very small angle. Okay, so let me draw a line then here. And then I'm going to take my compass, and I'm actually going to draw a tiny arc of a circle. All right, there we go. And here's my skinny angle, and I've tried to draw the angle big enough that we can actually get a sense of what's going on. Because if I draw it really skinny, the picture will be useless. We won't be able to have any sense. So I want to say that this angle here, let me call it theta. Theta is a small angle. We're going to imagine it arbitrarily small. And let me take the radius of the circle, as it were, to be 1. So this line is 1, and this line has length 1. Now you'll see in radians, in fact, let me just use the compass again to make this drawing as neat as possible, given that I don't want a sloppy drawing to remove clarity here. The length of this arc here is going to be theta. And this comes from the fact that we're measuring theta in radians. So if this angle was 2 pi radians, which would be 1 whole revolution, for a circle of radius 1, the arc length, that entire circumference, would be 2 pi. So for a circle of radius 1, the arc length created by an angle theta in radians, that arc length is just theta. And that's a very nice property of radians. So theta is measured in radians, and this arc length is indeed theta. Now, let me drop down a vertical line to make our good old friend a right-angled triangle. And even though I've drawn this very magnified, this picture, it's still going to be a little bit awkward to see exactly what's going on here. This is a right angle. Here's theta, and let's just say, right, let's take the sine of theta. Well, the sine of theta will be this length of this side of the triangle divided by the hypotenuse, which is 1. Therefore, this vertical line here is nothing other than sine theta. If you watched the National 5 tutorials on trigonometry, you'll remember me using a circle construction with exactly this kind of idea to motivate the graphs of sine x and cosine of x for all angles. And we're doing a similar thing here, inscribing essentially a right-angled triangle inside a little sector of a circle. Cosine of theta will be the horizontal line here from the center of the circle to this point. That will be cosine of theta. And because the entire horizontal line here is a radius, is 1, this tiny length here will actually be 1 minus the cosine of theta. All right? Okay, that's fine. And what I want you to focus on now then is this part of the diagram, that we have the vertical green line here is sine theta. The arc has a length theta, and this tiny little line here is 1 minus the cosine of theta. And we want to imagine now taking theta smaller and smaller, and can we use this piece of geometry here to get an understanding of how would we approximate sine theta in terms of theta if theta is very, very small. So, what's clear is that as we make this angle smaller and smaller, these two lines will become essentially very hard to distinguish from one another. They're going to become more and more similar, and this tiny little horizontal line, which is 1 minus cosine of theta, is going to become harder and harder to even draw. So it's very reasonable for us to basically claim that sine theta for angles that are very small, where should I write this? Maybe over here. Sine theta at the very least should be some constant times theta, and we don't know what that constant is yet. And then there'll be what I'm going to call HOT, hot, and that just stands for higher order terms. And what I mean by that is there'll be higher order terms, powers of theta, which will be irrelevant compared to theta if theta is very small. Now, we know from the graph of cosine of theta, well, we know first of all that if theta goes to 0, we know sine theta will be 0. We know cosine of theta will be 1. So if we think of cosine of theta for small angles, it's going to start off as 1, because when theta is 0, cos of 0 is 1. Now, what will the next term be? Well, let me just say that the next term is, and excuse me if you think this is frivolous, but let me just call it apple, because it's actually easy to call it something, and why not call it apple? Where apple is very small, and can we get a sense of what apple is? Actually, we can, from a very nice little observation, which is that we always have in our back pocket, whenever we're dealing with sine and cosine, we always have this nice feature that, where shall I do this? Maybe over here. We always have that sine squared theta plus the cosine squared of theta is equal to 1. That's always true. That's just Pythagoras' theorem. And for these very small angles, let's have a look. Well, sine squared theta, the leading term of it is just going to be a squared times theta squared. I'm not worried about those higher order terms. I just want to take the leading terms here. And then cosine squared of theta is going to be 1 plus this unknown apple, this small thing that we know nothing about, squared. And this has to equal 1, all right, for any theta. And let me just, given the apple is very small, let me just take that leading term there. So I have a squared theta squared I'm going to multiply out this squared bracket. I have 1 plus 2 apple, and again, apple squared is going to, I'm just going to throw that into this HOT higher order terms that we don't care about. And there's some from sine squared theta that come from this HOT. Apple squared I'm going to just throw into this basket of fruit, no, of terms which are higher order that we don't care about. And this has to equal 1. And now you see a little bit of magic happens, which is not uncommon in maths. We already have 1 on the left-hand side, and we have 1 on the right-hand side. So this apple actually must cancel out this a squared theta squared term. So we can actually determine apple. So it must be true that a squared theta squared plus 2 apple is 0. So apple must be minus a squared theta squared divided by 2, which is really a nice result, and it's interesting. It's interesting for the following reason. So what we have then is that cosine theta for small theta is 1 minus a squared theta squared divided by 2, and I'm just going to write plus hot, higher order terms that we don't care about. But this makes a lot of sense, you see, that when the angle's really small, this vertical line is essentially has a size which is the same order as the arc length of the which is the angle in radians. Okay, so sine theta and theta are sort of like equivalent in size as theta gets really small. But do you see how this little length here, which is 1 minus cosine of theta, 1 minus cosine of theta is a squared theta squared over 2 plus higher order terms. Do you see how this is not equivalent to these other two lengths? This is actually getting smaller as theta squared. So to give you an idea of this, imagine if the angle was 1,000th of a radian. Then this length would be 1,000th. This sine theta, we're saying, is some number that we haven't determined yet, a times theta. This is of order 1,000th. But do you see how this little horizontal line here, because it's theta squared, would be 1 over 1,000th squared, would be a millionth. So as you make the angle smaller and smaller, this little horizontal bit disappears far more quickly than these two lengths. And because of that, for very small angles, it must be actually that these two lines become equal in length. The way to think about that is, if I want to go from, say, this point to this point in a atomic-sized motor car, imagining this is all tiny, if I drive along the arc, I travel exactly a distance theta. If I travel along these two lines, I go sine theta this way, and I go 1 minus cos theta this way. But what we've argued is that for theta very small, this length becomes negligible compared to this length, because this length gets smaller as theta, and this length gets smaller as theta squared. But the journey length must be the same either way for the angle essentially becoming vanishingly small. Therefore, sine theta must be equivalent to theta for theta arbitrarily small. So in other words, a is 1. And we can argue a is 1 again because this horizontal line, which could have maybe given some contribution to a length that's of order theta, doesn't, because it's actually always much smaller. It's theta squared. So the net result of this rather delicate analysis is that sine theta for theta very small is just theta plus higher order terms. And we can just read off then that cosine of theta for theta very small is 1 minus theta squared over 2, because a is 1, you see, plus higher order terms. And it's really interesting to work out these higher order terms. It turns out they have a very nice structure, but it's not relevant for us now, so we don't have to worry about it. But this is actually by far the hardest bit of the derivation, this graphical sort of proof. But we have what we need, which is that sine theta is theta plus higher order terms for theta very small, and cosine of theta is 1 plus terms which are of order theta squared. So going back to this, we know that we're looking for that term delta x, term of size delta x coming from here, which will ultimately give us the derivative. So if we continue now with the derivation, so if I just go from here up to here and just carry on, so we have the f primed of x then is sine of x times cosine of delta x, where delta x is really small, so I can use this formula here. It's 1, and I'm actually going to lump this theta squared as higher order terms. It's 1 plus higher order terms, and by that I mean terms that are smaller than something of size delta x, because the next term would actually be delta x squared over 2, but I don't even want to be bothered to write that because it's not important for us. It's too small to matter. And then I have plus cosine of x times sine of delta x, which we know is delta x plus higher order terms. And then I have to subtract sine x from all of that and divide the whole thing by delta x. So let me just see what I've got here. So just to remind you, higher order terms means things which are delta x squared or delta x cubed or delta x to the fourth and so on, which are irrelevant, because when we divide those by delta x and take delta x to 0, they will vanish. So I have sine x times 1 minus sine x, so this term cancels this term. I have higher order terms that are going to be 0 once I take this limit of delta x to 0. I have cosine of x times delta x. Now cosine of x times delta x divided by delta x is just cosine of x. And I have more higher order terms, delta x squared and so on, which when I divide by delta x and take delta x to 0 will vanish. So in fact, maybe the way I should finish this proof kind of satisfyingly, we have cosine of x delta x divided by delta x, and then we have these higher order terms divided by delta x, and we want to take all of this with delta x going to 0, and this all vanishes here, these vanish, and we're left with the result that we expected, because we were told in the last tutorial that the derivative of sine x is cosine of x. And there we are. That is the proof that the derivative of sine x is cosine of x. Now you might ask, what about the derivative of cosine of x? And I haven't left myself a huge amount of space here, but you know what? I think I can just about finagle a way to show you that if I just basically borrow everything I've done before. So how about the derivative of cosine of x? What if I just do everything in green involving cosine of x? Okay, so imagine we wanted to look at a function f of x is cosine of x. The derivative would be the cosine of x plus delta x, which is f of x plus delta x minus f of x, which would just be cosine of x, all divided by delta x. And then using the double angle formula, the addition formula for cos of a plus b, I would have cosine of x times cosine of delta x. I would have minus, maybe I should just write that again there. And then remember the addition formula for cos of a plus b is cos a cos b minus sine a sine b. So I would have minus sine x times sine delta x, and then I subtract cosine of x. I then have exactly the same as before. You see that all the action is in these cos delta x and sine delta x terms. So all of the difficult part of the derivation is exactly the same. We just need these two results here. So when I go back to doing my derivative, instead of having sine x times this 1 plus hot, the 1 plus hot is the cos delta x. So instead of having sine x multiplying that, I have cos x multiplying that. And with this bit here, this delta x plus hot is what we got from the sine delta x. That's the same, but instead of having cos x multiplying that, I have negative sine x. These are the same, and then I just subtracting cosine of x from everything at the end. So the HOTs don't matter, that's all going to go to 0 as delta x goes to 0. I have cos x times 1, take away cos x, that vanishes. So the only term I'm left with then is negative sine x times delta x. The delta x vanishes and I'm left with negative sine x. Okay. So these are like, I'm just going to put sort of all of this in some weird kind of brackets here. This is like a ghost derivation in the background. This is what a quantum computer could do. See, it can compute different sets of functions at the same time using quantum entanglement. So we're doing a quantum entangled derivation here where we're just doing sine and cosine at the same time. And the cosine derivations in green in these crazy square brackets. So, you know, some people would be shaking their heads in annoyance or astonishment possibly, but actually I hope that's pretty clear. So at least it's a good way to save paper, that all of the mathematics and intelligence and creativity for the derivation that we did for sine x is exactly the same for cosine of x. The only difference is that we're just using we have slightly different things that come out of the addition formula. And you can see actually what's really nice here, ultimately. I mean, you know, when all of the dust settles, all of the action in this derivation is in these terms here, because when delta x is very small, basically cosine of delta x is 1 plus higher order terms. There's nothing going to come from here for the derivative. And then when delta x is small, sine delta x is basically delta x. So actually, this term here is already the derivative of sine x, and this term here is already the derivative of cosine of x. We just had to work a little bit harder to kind of be clear that, you know, that these actually do come out once the dust settles as the answer. But you can see already here that's where it is. So in a beautiful kind of way, the form of the addition formula that we looked at in trigonometry contain within them actually already the answer to the question, the derivatives of sine and cosine, which is a kind of a very cute observation. So there we are. That's the derivation of the derivative of sine x being cosine of x and the derivative of cosine of x being negative sine x. I hope that was useful, interesting and clear, and it's really optional. It's for those folks that like to see the proofs you know, behind the scenes. So the next tutorial back in the calculus series, I'm going to do a little bit of formal calculus. We're going to be looking at some language that is used, some sort of terminology. We're going to be looking at some new notation, which is the Leibniz notation, because we've been using the Newton notation up till now. And we'll also be talking about this superb piece of mathematics called the chain rule, which is, you know, I'm not even going to gush about here. I'll gush about it in the next tutorial, but it's really powerful and very beautiful. So until then, I wish you well. Thank you for your attention in this rather difficult tutorial, and I will see you next time.